All right, folks, today we're going to talk a little bit about coordinate systems. And really, this is asking the question, where are we? And that's what we're going to be focusing on with this video, because I think a lot of people get stuck and say, ooh, thinking about different coordinate systems, it's really a pain in the butt here. And converting between the two, blah. No, we don't have to do any of that. We're going to make this simple, easy for what we need to know for this course. So let's get into it and think about different types of coordinate systems. All right, so usually when we're thinking about plotting things, so for example, in a two-dimensional set maybe, we could be thinking about plotting our point here, -3, 2. So we've got -3 in the x direction, +2 in the y, and if we draw lines out from it, we can plot where that point actually is. You did this probably years ago, and it's something that's probably familiar. You did this in physics, I'm sure, at some point. Maybe not in the same way, but making plots with x and y and saying, where are we on that plot? We'll have to be a little bit more thoughtful because now we're dealing with three-dimensional systems, but really in Cartesian coordinates, it doesn't change much because if we have a point that we want to specify in three-dimensional space, well, then we just need to let us know what is the x value, what is its y value, what is its z value. So in this case, we'd be thinking it has an x coordinate of 3, a y coordinate of 5, and a z coordinate of 4. This tells us where we are in three-dimensional space. So simple, easy, nothing crazy here. And this is probably how we've done a lot of plotting. The problem that this comes into is this can be a real pain in the butt with regard to mathematics, especially when we're thinking about, for example, the Schrodinger equation, where we end up having to do a lot of second derivatives with respect to coordinates. We find out that really using three Cartesian coordinates is not the easiest system of reference to use here, so we need to make a shift. The shift that we're going to do is to that of circular, or in 3 dimensions, spherical coordinates, also sometimes referred to as polar coordinate systems. So if we want to think about a point in 2-dimensional space, point P here, another way we could do it, instead of saying where is it in x and y, we could say how far is it from our origin, so give us a radius from the origin, and define an angle away from the x-axis, theta, to tell us where we are in our 2-dimensional space. So again, still 2D, we've still got two variables that we're going to work with. Here now we're just saying how far am I, r, and at what angle am I, theta. We can do the same thing with 3-dimensional coordinates. We still have an r and we have a theta term, but they're a little bit different. So now we're saying our theta is how far down from the z-axis are we. And we could think about our third coordinate for 3 dimensions as this phi or phi, depending on where you faux from. So when we're thinking about this, this is now our coordinate system that we could use. So using spherical coordinates, I could say, how far am I from our origin? It's a radius. What angle down from the z-axis do I have? Theta. And what angle do I have with respect to the x-axis? So phi there. So again, using 3 coordinate system here, just now with an r, a theta, and a phi. So nothing really changed here. It's just now a new system that we're going to use to better describe it, now using circular nomenclature, radius, and angles, rather than Cartesian coordinates. This is going to turn out to be much nicer when we'll deal with the actual mathematics, which is kind of funny when I show you the Hamiltonian operator. So if we go back to the Schrodinger equation, we saw the Hamiltonian operator for Cartesian coordinates. Here it is in polar coordinates. And yeah, that is a lot going on here. So I know it does not look simpler. There's a lot of things that we're seeing here. Now we've got all these wonderful trig functions. The reason those trig functions came in is because when we convert from our Cartesian frame, now we get these sine theta, cosine phi, sine theta, sine phi, cos theta terms that come in. That's because of the conversion that we do from Cartesian to polar coordinates. Don't worry, we're not going to have to do this. But trust me when I say it's going to make things a lot easier, because when we deal with an atom, remember, the way we're commonly thinking about atoms is that they're spherical. They have a certain symmetry that's going to be nice for us to recognize. So when we're dealing with something, the spherical symmetry of our spherical coordinates is going to actually come in handy and make our lives easier. Again, we're not going to worry about the math here. I just wanted you to see these so that you would know what we're talking about when we hit them. All right, so that's what we got with our coordinate systems that we need to know for here. As always, let me know if you have questions, concerns. We'll get you straightened out. And until I see you next time, be excellent to each other.